ladies and gentlemen. After this wonderful conference dinner, it's really not easy to be here. It's really too early, and I'm sure that it is also not very easy for our today's plenary speaker, Maciej Zworski, also to give this plenary lecture today. Anyway, on behalf of the organizers of this meeting, I am really pleased that he accepted the invitation of the organizers of this meeting. We should know about him that he is recently a professor at the University of California in Berkeley, and his main interests in mathematics are microlocal analysis, scattering theory, and partial differential equations. He was born in Poland, in Wrocław, and he received his graduation from the Imperial College in London and from the Massachusetts Institute of Technology. He is the Fellow of the Royal Society in Canada, a Fellow of the American Academy of Arts and Sciences, and he received the Coxeter James Prize of the Canadian Mathematical Society in 1999. He was also an invited speaker at the International Congress of Mathematicians in Beijing in 2002. His book, entitled Semi-Classical Analysis, which was published in 2012 by the American Mathematical Society, is really one of the most influential books of the subject. And now we have the luck and the pleasure to welcome him on the stage, and we are really looking forward to listening to his talk. Professor Zworski, the floor is yours.
So I will talk about, well, my title is From Classical to Quantum and Back, and I will explain what I mean. So I work in partial differential equations in sort of postmodern quantum mechanics. And we, in this subject, use methods from dynamical systems, but always treated them with a certain amount of fear as a black box without knowing what's inside. And that's what I would say is from classical to quantum, that you want to understand quantum system using some classical dynamics. So let me start with some example of classical dynamics. So here are two billiard tables, and perhaps looking at them, one does not see a dramatic difference between them, but if one looks statistically, namely starts with 10,000 balls traveling and reflecting from the walls, then the one on the left is very different than the one on the right. The one on the right is very chaotic in the sense that eventually the balls actually are equidistributed both in position and in velocity, while on the other side the motion is very organized forever. So actually this equidistribution in position and velocity can be seen here, that as time goes on, basically the proportion of the balls inside of this rectangle is essentially the area of this rectangle. It sort of stabilizes here somewhere. And this is the histogram of the directions of the velocities. So again, you see that it more or less becomes equidistributed. So in particular, this flow is ergodic in the sense that any invariant set is either, with respect to the flow, is either the whole set or it measures zero. So here, of course, we're looking at position and the circle of possible directions. So a mathematical manifestations of ergodicity, one of mathematical quantum mechanical manifestations of ergodicity is so-called quantum ergodicity. So here is my billiard table with all these balls here sort of equidistributed after some time. And this is an eigenfunction of the Laplacian, a very high one. So the frequency is 1,000, so the energy is about 1,000,000 here. It's computed by Barnett. And we're looking at properties of these eigenfunctions. And the theorem, which started with Schnirelmann, and I actually worked on this with Zeldich, that was for instance, for this kind of billiards, that exists, if I look at the complete sequence of eigenfunctions, there exists a density one sequence of indices, such that for any function which is continuous on the billiard table, if I look at this observable, this converges to the average of the function. So what this means that except possibly of some density zero sequence, you have equidistribution in position, as somehow this picture here suggests. In fact, there is a finer version of this result, which in fact is the only way in which this can be proved, or is, well, how we know, the only way we know to prove such a statement, is to actually go to phase space, in the sense that we want to actually localize our eigenfunctions not just in position, but also in velocity, and in which case, so I will explain what this means. This is a quantization of a classical observable, and if I apply this quantized observable, so this is now an operator applied to this eigenfunction and paired with the eigenfunction, then it converges to the average of the classical observable over the billiard table across the circle of directions. So let me just give a very quick course in microlocal analysis or semi-classical analysis, but it should not be anything different, perhaps except for notation, than what one sees in any undergraduate course in quantum mechanics. In quantum mechanics, we look at the classical picture, position and momentum. We have some wavelengths, effective wavelengths of our problem. It could be Planck constant divided by square root of 2 times the mass of the particle, but it could be some other parameter, but that's the effective wavelengths of the problem. Classical observables are functions, such as, for instance, the energy, psi square kinetic energy plus V potential energy. And quantization, in sort of undergraduate quantum mechanics, consists of replacing position by just multiplication by a function of position, and replacing momentum by h over I times the derivative. So this I is here to make this self-adjoint. So this was the quantized classical observable that appeared in my previous slide. Well, those are the examples, as I said, from undergraduate quantum mechanics. Quantization of xj is just multiplication by xj. Quantization of momentum is just differentiation with this extra factor here. And people may disagree as to what constitutes a quantization of classical observables, but everybody, as far as I know, agrees that in any quantization procedure, commutator of 2 quantum observable should be a quantization of the Poisson bracket of the 2 classical observables. Now, the Poisson bracket, here is the Euclidean version, but here is the connection to dynamics. Poisson bracket of AB is the Hamilton vector field of A applied to B. That's a definition here. And the Hamiltonian flow is the flow describing classical motion. So the standard example would be if I take my A to be psi square. So I forget constants, V of x. Let me put 1/2 here. In this case, HA will be psi dx minus V prime x d psi, and the trajectories are x dot is equal to psi double dot is equal to minus V prime of x, and that's, psi dot. That's just Newtonian equations of motion. So this relation, gives, classical quantum correspondence. So now, to give with these definitions, I recall a version of this theorem. So this is a version due to Zeldich. The case of compact hyperbolic surfaces. If I take an observable, quantized classical observable applied to an eigenfunction, and I look at the L2 norm squared of that, this along a sequence of density 1 converges to the average of absolute value A squared. And here we quantize it at the frequency corresponding to the eigenfunction, frequency of the eigenfunction, so that means square root of the eigenvalue. And this is the Cos-Sphere bundle. So this is a version not with a boundary. So now here is some recent progress on this due to Dyatlov and Jin and Dyatlov, Jin and Nonnenmacher, which states the following thing. If I look at Zeldich's theorem here, one sees that along this sequence of density 1, this quantity here, this is bounded from below by on any set, bounded from below for any A, obviously by some constant depending on A. This theorem says that actually one doesn't know about the limit, but one knows that this quantity actually is bounded from below for any eigenfunction by a constant depending on A, as long as the support of the classical observable intersects the cosphere bundle. So in other words, just as in my picture before, there are no white spots for any eigenfunction of a strongly chaotic system in dimension 2. So this used results, earlier results of Dyatlov and Zal, and a crucial component was so-called fractal uncertainty principle of Dyatlov and Zal and Brugge and Zal. So I now want to say a few more words about this, quantization and estimates. How does one prove theorems in this business? How does one relate classical flows to properties of solutions of PDEs, simple PDEs such as the Laplacian on a manifold? Well, I quantize some observable. For instance, this observable here will be quantized to minus, by the procedure I described, to minus h squared Laplacian plus v of x. This would be the quantization of this of h a is equal to, other way around, I suppose. Never remember. Well, and we would like to estimate. U in terms of the right-hand side. That's what one does, in PDEs. And the simplest estimate, of course, if we could estimate U in terms of F, we may not be able to do it globally, but we may do it in a chunk of phase space. So this A would localize my function U, both in position and in frequency. And you may then have an estimate like this when U is localized, even if you don't have a global estimate. And this estimate actually holds in the case when the support of my classical observable is disjoint from the place where P is equal to 0. In this case, this is basically like algebra, and in fact not very far from being like algebra. If P does not vanish, you can divide by P, and then you have an estimate on U with respect to F. Well, it may not be true everywhere, but it is true indeed in places where P does not vanish. That's the sort of basic estimate. Things are more interesting when we are inside of the place where P vanishes, in which case one has propagation estimates, and that's what relates properties of, say, eigenfunctions to the flow. And the basic estimate is the following. If I want to estimate my function here, I need to now put in some information about it in the past as far as the flow goes. So as long as every point here is controlled in a sense that comes from on a trajectory of the flow, from some point where B is non-zero, one can estimate it. And the easiest case to check it in is simply take the operator, take the observable psi1. It is then quantized to h over I derivative with respect to x1, and you can check this estimate, including the necessity of this constant here. So here is now an example, another example of use of or connection between classical dynamics and properties of solutions of PDEs, namely decay of waves. So here is a long equation, but what it is just the wave equation outside of some obstacle in three-dimensional space. And with initial data, extremely nice, compactly supported smooth functions in a compact set. And one could ask then the following question. Suppose I look at energy of a solution in some set. So of course, if A is all of R3 minus the obstacle, the energy is conserved. But here, we are interested in energy in some compact set K, and we would like to ask the question, will the energy decay exponentially in a compact set. And, you know, this is supposedly important in applications because, you know, if you build a plane and you don't want to see it, you want the waves generated by it to decay exponentially, something like that. I don't know. But mathematically, it's a clear statement, namely energy. I ask, will energy decay exponentially with a control by the initial energy? And a classical result in this business is that it is indeed exponentially decaying if and only if the obstacle is non-trapping. And that's a statement in classical dynamics. An obstacle is non-trapping means that, I'll have a picture in a moment, is that, say, an obstacle like this is non-trapping because any ray hitting it bounces back and never comes back. But if I throw in, say, another obstacle, well, then suddenly this one is very weakly, but yet trapping, because this trapped orbit here never escapes, reflects forever. And in this case, if this wasn't here, we would have exponential decay of energy. With this thing, the energy does not decay exponentially, at least as long as we demand that we want this decay without paying any penalty as far as this energy is concerned. So this is an old result, actually, Ralston's thesis 50 years ago, but it's still alive. So, for instance, many adaptations in various different settings, for instance, relatively recently by Zworski in the setting of general relativity. And the other direction comes from applying propagation of singularities using various approaches, either Lax-Phillips or Weinberg or some other way. But and actually, there's some motivated, because Spence is actually a numerical specialist, so motivated by some concrete numerical problems, there has been progress on finding out what is the best constant here, depending on the obstacle and the compact set at high energies. So I recall the local energy decays exponentially with control by the energy here, if and only if the obstacle is non-trapping. So here is an example of a non-trapping obstacle. Well, that was my sphere here. You can sort of see that, well, waves just go by. Here I have a trapping, actually sort of weakly trapping obstacle, sort of a little bit like this, but with a little bit of extra. And you can see this wave here sort of sloshes around and will not decay exponentially as long as I am insisting on controlling it by the energy of the initial data. And this is based on one of the sort of highlights of microlocal analysis from the glory days of the 70s and 80s, and the work of this and other authors. And I just want to mention, because that's actually related to what I will talk about later, that if the trapping is hyperbolic, which sort of here, there's some problems with eclipse condition being violated, but more or less you have hyperbolic dynamics here. You do actually still get, under some assumptions, exponential decay, dynamical assumptions involving things known to ergodic theorists such as pressure and so on. But the difference is that here you have to pay some penalty, you have to add some derivatives in estimating this in terms of initial data. So I want to just say one thing. So in the case when the obstacle is non-trapping, such as the sphere, we can actually expand the solution of the wave equation in terms of modes, except these modes, lambda j's, are now complex. And they have a rate of decay, and a rate of oscillation, and a rate of decay. And of course, the distribution both of the rates of oscillations and decay is related to the dynamics of the obstacle, dynamics of this broken flow for the obstacle. So these lambda j's are called the scattering poles, and I won't say much about them. It's very difficult to define them dynamically, even though numerically you can actually compute them by solving the wave equation, doing harmonic inversions from this lambda jt. I tried to do it myself using apparently the best current code from MIT, of all places, but I was not very successful myself, but I've seen papers where success was claimed. But mathematically, it's nicer to describe it using the stationary wave equation, which is simply the wave equation where we take the transform, Fourier transform in time, and that is an equation like this, that we solve, we basically look at the green function for the obstacle problem. Of course, there are many possible green functions here, but we fix one if we demand that for imaginary part of lambda bigger than 0, this maps L2 to L2. And then there is only one. And it turns out that this G has a meromorphic continuation if you fix x and y in lambda, and these lambda j's are the poles of this. Okay, and I have here, sorry, this is, sorry, well, apparently this could not be regulated, the sound. So this is now not an obstacle problem. These are the resonances of scattering poles computed by David Bindle for this potential on the line, and this is how they sound. So I'll play it one more time. You see, the frequency increases, but then imaginary part produces damping. So in principle, what would be nice that you could like close your eyes, hear this, and then draw the potential. Nobody knows how to do it. But that's an interesting problem, which is important for various, I mean, the reason that Bindle did this, well, he did this just to humor me, but his day job was computing resonances for MEMS, microscopic electromechanical systems. So I now come to classical dynamics again. So this is the picture from the beginning. And I won't talk about billiards in this talk, but it's easy to show them as examples. So here we had our billiard table, and we had a classical dynamical system. And in our classical dynamical systems, after a long time, we have this equidistribution in position and in velocity. And typical questions one can ask here is, how long do we have to wait to have uniform distributions? Are they periodic orbits, and what information do they contain? So, you know, how long do we have to wait if we knew that the decay towards this equilibrium is exponential, then roughly the time to wait would be determined by the rate of exponential decay. And in fact, for a certain billiard, that progress on that has been made recently by Baladi, Demers, and Liverani, exactly about the rate of decay for billiards. But I will talk about the dynamical analog of the Riemann zeta function, because it turns out that when it comes to both questions like the rate of decay, say if you want to compute it numerically, or questions about distribution of length of closed orbits, it is a very useful tool. So what is it? That's the Rouelle zeta function, which basically is the same as the Riemann zeta function, except that you replace primes by the length of primitive closed trajectories of your system. So here is that example before. In this case, even though it's very chaotic, there are plenty of periodic orbits. So I drew one here, which is just a bouncing ball between the two walls, and that trajectory is extremely unstable, because the one which is very close to it immediately goes somewhere else after a few iterations. But it turns out that information about the length of closed orbits, and also some infinitesimal information about this rate of divergence for nearby trajectories, can be used to construct zeta functions, which then contain information about, for instance, the time that you need to return to equilibrium. And as far as I know, that is the most effective way of computing that and other things. So here's this zeta function. I don't put a -1 here because, it doesn't matter really. And this is the dynamical zeta function. The primes are replaced by e to the L gamma, the length of a primitive closed orbit. So primitive simply means that I have a closed orbit. I count this length, the first length only. I don't count include the length of the iterates. And as I already said, so this is just to reiterate it, the zeros and poles of this all related zeta functions, which have some other stuff built in, do describe some information about that. Or, for instance, one can study the distribution of length of closed orbits using the properties of zeta functions. So zeta functions have been dynamical. Zeta have been studied by many authors. This is not an exhaustive list. Probably started by Selberg with the Selberg zeta function. And actually this picture here shows the zeros of the Selberg zeta function for a sort of a torus with a big funnel attached to it, a surface of constant negative curvature, and this you change the length or you change the angle, you see a very different distribution of zeros of these zeta functions. And Smale conjectured 50 years ago or so that for Anosov flows, actually he conjectured for a class of axiom ace flows, that this zeta function should be meromorphic in all of the complex plane. And and he wrote, I learned this from a paper by Giulietti, Policott, and Liverani, but I did, of course, check in the original paper that he did actually write this. He doesn't look particularly shocked, but I did feel that I should at least include a picture of one Fields medalist in my talk. So, since this is for Anosov flows, I will tell you quickly what it is. An Anosov flow is a flow, let's say, we are in a situation of a surface. So on a surface, Anosov flow takes place on points on the surface plus the direction. So it's 2 dimensions plus the circle. So it takes place in 3-dimensional space, like this room. And the flow is Anosov if every point of at every point, the tangent space has a decomposition into neutral, stable, and unstable directions. So this means if this is my space, and this is a point, and this is the tangent space, then we have 3 directions. One is neutral, this is the direction of the flow. One, let's see, this one here, say, is stable, so this means that my flow converges to this trajectory in this direction. And one of them is unstable, we diverge. This is a very special condition, very strong condition. It does appear, however, in interesting situations. I must confess that I personally am really only familiar with this example, but my dynamicist friends tell me that there are lots of Anosov flows of various kinds, but that's one of the nicest one for sort of regular mathematician. So the theorem, actually, the conjecture of Smale in the case of Anosov flows was proved by Giulietti, Liverani, and Policott. And Dyatlov and I, we gave what to us is a very simple microlocal proof of that theorem. And that was somehow going back to classical from quantum, because we used the methods which were developed to use classical dynamics to prove things about quantum systems, and now we use methods for study quantum systems to actually prove something about classical systems. I never expected this would happen, to me at least. So, of course, the proof has a long tradition. The crucial component is the work of Foer and Szestrand, who explained microlocally the spaces which had already appeared in dynamical systems, in particular, among other works, in the work of Blanc, Keller, Liverani, Baladi Tsuji, and other authors, the so-called anisotropic Sobolev spaces. And those are inherently microlocal because these are spaces where the regularity changes depending where you are in phase space, depending on the properties of the flow. So I won't be able to say much in detail about it. And the other technical component were tools from scattering theory, namely radial point propagation estimates, which were due to Melrose, and they were used in many settings by Vashi. in the works of Melrose and Vashy, the radial sets, whatever they are, they're sort of the attractors of the flow, if you like, in this setting. They are always very regular in scattering theory, typically. But here they are not. I mean, there's some nasty sets, you know. But these estimates are, you know, you just go through the proof and you see they work even for nasty radial sets which appear in the setting of dynamics. So axiom A flows, generalized Anosov flows, I won't say give a definition, but roughly speaking, you don't have this decomposition everywhere, but you have it on a sort of the trapped set or the non-wandering set, some compact set. So that was actually the original setting of Smer's conjecture. And that was actually proved using microlocal methods, developing further this type of estimates by Dyatlov and Guillermo. And this is kind of a cartoon description of how these things go. Well, in scattering theory, we look at, classically, we look at some Hamiltonian like psi squared plus v of x and look at the energy surface. So this energy surface, typically, this potential here would be some potential like this in dimension 1. And then say this is my energy E. If I look at psi and x, so basically I look at the, in dimension 1, it's just the level set of this, then it looks like that. That's the set where P vanishes, psi squared plus V minus E vanishes, whoops. And you go to infinity in X. You have infinity in Xi, but it's kind of a technical nuisance because Xi never goes to infinity here, but we still have to do this because, you know, it's just one of those boring things about PDEs. But it's really what happens as X goes to infinity matters. For Sjöstrand somehow reinterpreted the anisotropic Sobolev spaces of dynamical systems by looking at the generator of the flow as a PDE. So of course this is a very silly PDE because you have a if my flow, so I have some flow, phi t is generated by some vector field. We now define an operator P, which is 1 over IV. This 1 over I is because we are always sort of quantum mechanicians wannabes, and if there is an invariant measure, then this would be a self-adjoint operator. And then, if I look at what does this quantize? Well, this quantizes a function P, which is just a at x psi, which is just a covector psi applied to the vector v at x. And that is now a non-compact, except in dimension 1. This is a non-compact characteristic surface, and your scattering now takes place in psi equals to 0. In fact, this is a much simpler situation than scattering, because your x is compact. You don't have any of this kind of PDE nuisances as we have here. And I somehow, if one were to say a word about our proof of the meromorphy of the zeta function, it was based on sort of propagation from the stable to unstable things. If I look at P equals 0, characteristic set, we can ask what is the trapped set? Like in the setting that I had in the obstacle, what is the trapped set for this Hamiltonian? Well, if I look back at the definition of Anosov flow, if I insist that this is equal to 0, I have to say, what is the flow? What is HP? Maybe can I flip it? No, maybe not. Well, HP, the e to the THP, is given of x and psi, is just a symplectic lift of the classical flow in the base, and if I am the characteristic variety where this is 0, this means that I kill the direction of the flow. But if you kill the direction of the flow, everything else will either go to infinity in a positive or negative time direction. So the only trapped set is the zero section. It's psi equals to 0. That is the trapped set for this problem. And in the setting of axiom A flows, it all became much more complicated because now you have this compact set, so you have both, escape here, but you also can have sort of escape to infinity. You are now in a more complicated situation than the scattering theoretical situation. So in a way, we have the following kind of table of how the concepts from scattering theory or microlocal analysis can be adapted and used in dynamical systems. Well, we have the flow. That's our starting point, which is generated here. Oh, sorry, this is V by X. Well, our stationary wave equation is now the eigenequation for this X here. And I put an I here because I say I kind of like to have it close to Cepheid joined if it could be. If it's on functions and you have an invariant measure, then this is a Cepheid joined operator. So we have this problem here. But you see, we know already that this problem really, from the spectral point of view, is not that interesting. We had to go to some meromorphic continuation of the green function to see those resonances which appeared in the expansion of waves. It was this sound that I played. So, of course, here it also has to be understood in some different way, or one should look at the resolvent of this and continue it meromorphically. The energy surface, well, it's the energy surface of this guy now, which is non-compact. Just like this one here was not compact as far as X goes. Here is non-compact as far as Xi goes. Scattering in the standard sense of X going to infinity, here it's just a study of singularities of things. That's the properties of Xi going to infinity. That's where the scattering takes place. The correlations, well, I wrote it in this rather strange way. Well, if I want to look at correlations, well, we evolve some observable using, say, the wave equation. This is the wave propagator. And then you pair it against another observable. So this was when one hears this sound, I suppose, in some schematic way, this would be the initial data for this computer playing the music, and G would be our ears. And that's what we register. That's the correlation. In classical dynamics, it was exactly the same thing. You see, this operator I write in this complicated way, but in fact, e to the, so of course that's, i's cancel, so this is just e to the minus tx, but this applied to a function, that's just a pullback by the flow. So it's actually a very simple propagator, but it turns out that studying it using PD method that was maybe pioneered by Tsuji is useful. Exponential decay of waves, what I discussed here, that is related to exponential decay of correlations. And in fact, one can have proofs which do it using the ideas from here. We always have a trapped set here, because as I just told you, zero section is a trapped set at energy zero already. So you can't expect this kind of exponential decay controlled by energy of initial data. But if you pay a little bit of a price for some classes of Anoso flows or axiom A flows, such as, say, contact flows, that's a result of Tsuji, you have exponential decay of correlations. And scattering resonances are Polycott-Rouel resonances which appear in expansions of correlations. Even though I have to say that these guys here, can be observed, and they're observed all the time. These guys here have not yet been observed in nature, but on the computer they have been observed, but not in nature as far as I know. Reason being that even though Anoso flows are this beautiful mathematical model, you would have to have an extremely controlled and protected system where somehow viscosity or damping will not come in and dump everything exponentially before you start seeing some finer feature correlations. But maybe, scattering resonances have been present in quantum chemistry since the 30s, but actually only in the 90s they've been people started observing them all the time. If you want to see a scattering resonance yourself, you can do this. I mean, I'm sure people know about this, how you have exploding grapes in microwaves. David, you've never done this? No? Take a grape, cut it in half so that the skin is still attached. Put it on a saucer, which is slightly concave so that they don't fall apart. Put it in a microwave. And it's safe. I did it at MSRI, though, not at home, because, it explodes. And last year, there was actually an undergraduate research project at Brock University in Canada, published in Proceedings of National Academy of Sciences, where they explained this phenomenon using something called the Mie resonance of spheres for the dielectric materials. So this you can see a lot of. This is very tricky. But we still study it because, it's present in the literature. So here is an example of a sort of easy to state result using this method, another one. Suppose you take a compact Riemannian surface of negative curvature, and, topologically, the only thing that it has is its genus, so it's a number of holes in this surface. And what we showed with Dyatlov is that the order of vanishing of the zeta function at 0 for this Riemann surface, so actually it's a slightly more general term, but state this, is equal to 2g minus 2. So in particular, it solves the following ridiculous inverse problems, namely that the length spectrum of a negatively curved surface determines the genus. So I give you infinitely many numbers, and I get one number. Hey, I mean, it's a mathematical result, but and actually, just one point comments. In constant curvature, this follows from the Selbach trace formula, was noted a long time ago. Even when the boundary is non-empty, even in a constant curvature, a result like that was not known until recently, and Hartfield generalized our result to the case of boundaries. So I want to finish by stating a few results which, among other things, use this micro-local methods, but of course use also all sorts of other things. So first example is the work of Drouot, who considered the generator of the geodesic flow on the Anosov manifold, to which you add a sort of viscosity terms, which is a spherical Laplacian on the cosphere bundle. Okay, so this is a constant coefficient. So this is like you would take the Laplacian on the fiber of the cotangent bundle with the coefficients given by the base, and then you look at the spherical part on the cosphere bundle. This operator for nu positive has a discrete spectrum because it's a hyperelliptic operator. And what Drouot showed is that when nu goes to 0, the eigenvalues, so this is a hyperelliptic operator, so it has discrete spectrum, they converge to these Polycott-Rouel resonances. What people expect, and there is literature in the probability community, but PDE people treat probabilistic methods with suspicion generally, so I haven't really looked at those papers. But when nu goes to infinity, you expect that this operator should somehow, after some rescaling, converge in some suitable sense to the Laplacian in the base of the manifold. But the results are not yet satisfactory. Actually, related thing, you can look at the Witten Laplacian. So this is nu is now essentially the semi-classical parameter in the Witten Laplacian. This is not quite the Witten Laplacian, it's conjugate to the Witten Laplacian. In this case, again, that's a result of Dang-Riviere generalizing earlier result motivated by some esoteric quantum field theory. They proved it that for a general Morse-Merle function, again, the eigenvalues, discrete spectrum of this operator converge to the Polycott-Rouel resonances of the gradient flow. And another interesting result is due to Bontonov-Weiss, who managed to define polyquadrual resonances for surfaces with cusps. The key thing here is that that's not an axiom A situation. There were applications to inverse problems in the case of hyperbolic trapping. And interestingly enough, there was also progress recently on the conjecture of Fried relating the values of some twisted zeta functions to purely topological objects. That's the work of Dang, Guillermo, Rivière, and Shen. They basically described in 3 dimensions. And perhaps the most impressive result using microlocal methods is that of Guillermo and Lefebvre, who showed the local rigidity of marked length spectrum for Riemannian manifolds of negative curvature. So this means if you have 2 metrics which are close to each other, and if the marked length spectra are the same, then the manifolds are isometric. That's a major advance. And there's also very interesting new work by Jezequel on trace formula for polyquadrual resonances for Anosov maps and flows. And there are many other results, so it's kind of an interesting thing to see where how far we can go with these methods in this business. Okay, so I'll stop here. Thank you very much for your attention.
What is the explanation of exploding grapes?
You know, you read the article because it's lots of physics language, but it's something called Mi-resonance. MI was a name, M-I-E. It's a German physicist of the 19th century. And it's some resonance of a sphere, but for a system, you know, and for Maxwell equations and so on. But all I can say that I understood was just the words and also the peaks, like the usual resonance peaks. And it's just a change of wavelength inside of the grape versus in air that produces this resonance phenomenon. So in principle, it should work with 2 spheres, but it's easier to do it with a grape, and you keep them touching the skin, not because that matters, but you just don't want them to fall apart. So they have. If you just Google it and online, if you're afraid to do the experiment yourself, you can see it. Yeah. Mm-hmm. Okay. Thank you.